In this video, we will implement GWO optimization algorithm using Python. Here you can see different steps used in this algorithm. First, we will initialize the population for the n agents in the search space randomly, and we have GWO as the search agents. After that, using objective function, calculate the fitness value for each agent in the current population. So here we are using the standard benchmark test function. Next, we will initialize the parameters. Then we have alpha, beta, and delta both. So GWO optimization algorithm we already discussed in previous videos step by step using numerical examples. For more details, you can check the link given below in the description box. So in this algorithm, we have alpha, beta, delta, and omega both. So we will consider alpha as the best solution, beta that is the second best solution, delta that is the third best solution. After that, we will start the main loop for this algorithm, and here we will repeat the loop until the stopping condition is met, and then for each agent we will update the position in the search space. And here you can see we have different mathematical models that we will use to update agent's position in the search space. After that, we will calculate the new fitness value for the updated solution, and again we will update the best, second best, and third best solution. Increment the counter, repeat the loop until the stopping condition is reached, and in the end we will return the best solution. Now we will implement this algorithm step by step. First, we will import numpy as np. Numpy means numerical Python. Using this module, we can perform different mathematical and numerical operations, and it also supports multidimensional and matrices and many more. Next, we will import kinter as tk. So we will use here a message box to display the final output from kinter. We will import message box, and we will also draw the convergence curve. So here we will import, and we will also draw the we will also draw the convergence curve. So here we will import matplot live.pyplot as plt. So using this we can draw the convergence curve. Next, we will define here initialization function that we will use to initialize the position for the each agent in the search space. So here we have input parameters, population size, dimension, lower bound, upper bound. So here we have different input parameters like population size, dimension, lower bound, upper bound. Next we will define the search space boundary, that is the length of lower bound. This condition then if is instance, then upper bound that is the object. Then we have class information list and np.nd array else 1. So we will check the search space boundary. We need all the solutions within the bound, that is the lower bound, and the upper bound that we will define in the objective function. Next, we will check if search space boundary is equal to 1, then positions we have. Here we will initialize the position randomly, rand, and here we have population size and dimension, then upper bound minus lower bound plus lower bound, else position we have np dot zeros. Here we have population size and dimension. So for I in range till dimension, we have the position, that is equal to random dot rand, and here we have population size into upper bound minus lower bound plus lower bound, and here we will return position. Here you can see we are initializing the positions randomly, but one difference you can see here. Here we are using the two-dimensional array, so it will generate the random value for specific dimension of I, but here it will generate the random value for all dimensions, and in the end it will return the position. And here you can see this condition, we need agent's value within the bounds, that is the lower bound and upper bound. Now we will apply Grey-Wolf optimization algorithm. So first we will define the main function, that is GWO, and using this we will apply this algorithm. So you can see the function name, we have GWO. So here we have different input parameters: population size, maximum iterations, lower bound, upper bound, dimension, and objective function. Now as you can see here, we have the first best solution, that is alpha, second best solution, that is beta, and third best solution, that is delta wolf. So initially we have the values for alpha, beta, delta, that is 0. So here we have alpha position, that is np dot zeros up to dimension, and its fitness value, that is alpha fitness is equal to, it is positive infinity. So like that we will initialize for the beta and delta. So beta position, initially it is np dot zeros, and its fitness value, that is positive infinity. Positive infinity that we already discussed in previous videos. Next for the delta position, it is again np dot zeros, and its fitness value, right now we have positive infinity. Done. Now we'll use this function for the population initialization. So we have positions equal to initialization, and here we have population size, dimension, upper bound, lower bound, and then convergence curve, that is np dot, right now it is 0. So as you can see here, first we imported all the important libraries, then here we initialized the position, and here you can see the solution boundary check whether they are within the bounds and not. Then you can see here the main function we used here for this algorithm, GWO Grey-Wolf optimizer, and then we have initially first, second, and third best solution 0, and fitness value is positive infinity. So initially the counter we have current iterations pose 0. Now we'll start the main loop for Grey-Wolf optimizer. Here while current iteration is less than maximum iteration, we will repeat this loop, and for now we will update the position for the agents for I in range up to positions dot shape 0. So you can see here shape 0 that we are using here to determine the number of rows in the array. So we have an array that is position, and using this we can determine the number of rows in this array. After that, boundary bounds for the upper bound, we need the solution within the bounds. So first we have boundary check for the upper bound, here positions and is greater than upper bound, then boundary check for the lower bound, that is positions is less than lower bound. Now the final position is equal to positions into, so first we have for the upper bound minus lower bound plus upper bound into upper bound plus lower bound into lower bound. Next we will apply the objective function on the position to calculate the fitness value. So here we have objective function that we will apply on the agent's position to calculate their fitness values. Now we will compare fitness values. If fitness value is less than alpha fitness value, then alpha fitness is the new fitness value. So if this condition is true, we will assign the new fitness value to alpha fitness value. Accordingly we will update, and accordingly we will update its position, that is equal to the new position. Next we will check if the fitness value is greater than alpha fitness value and it is less than beta fitness value. Here we have beta fitness value. Then the beta fitness value, then the beta fitness is equal to the new fitness, and beta position is the position. Next we will check the fitness is greater than, if the fitness is greater than alpha fitness and it is also greater than beta fitness and it is less than delta fitness, then we will assign delta fitness is equal to fitness and delta position is equal to the position of the new fitness value. Next we have a control parameter A. This parameter is used to maintain the balance between exploration and exploitation phases. Here we have the value for this, and A is equal to 2 minus 1, into 2 divided by maximum iteration. This parameter decreases linearly from 2 to 0 over the course of iteration. So here this is the control parameter. Now we will update the position for each agent in the current population, and here you can see we have different mathematical models that we will use to update agent's position in the search space. So for prey and circling, you can see the mathematical model. So here we will use for alpha, beta and delta, and then you can see the final position update is done by this. And you can see here we can calculate the value for A and C using these equations. So now we have the position update phase. So for I in range positions dot shape, this one is for the row. Next for j in range, and then we have the positions dot shape, that is for the column. So first we will take two random numbers, np dot random dot random. Next random number dot the value for a1, that is equal to 2 into a into r1 minus a. The value for a 2a r1 minus a. Value for c 2 into r2. So value for c1 we have 2 into r2. Next, you can see here using this we will calculate d alpha, then x1. So d alpha is equal to absolute c1 into alpha position, that is in j, minus positions in the ith row and the jth column. Next x1 is equal to alpha position in j minus a1 into d alpha that we calculated here. So here we did for alpha. Next we will calculate d beta and x2, d delta and x3, and then final position update x1 plus x2 plus x3 divided by 3. So again we need two random numbers, that is np dot random, second random number then value for a2 and c2 is again 2 into a into r1 minus a, done. c2 that is 2 into r2. Now we have d beta, that is equal to absolute c2 into beta position in j minus position, that is the ith row jth column. Then x2 is equal to beta position minus a2 into d beta. Now we calculate for the d delta. So again r1 we have dot random, another random number. Next random number value for A3 is 2 into A into R1 minus A. C3, that is 2 into R2. Then we have D delta, that is equal to absolute C3 into delta position minus positions in the ith row, jth column. Then x3 is equal to delta position minus A3 into D delta. Done. Now final position we have I comma j is equal to x1 plus x2 plus x3 divided by 3. Done. So here we will increment the counter, that is plus equal to 1. So it means in the current iteration we will add 1 and increment the counter. So next iteration would be 2 and up to so on. We have the maximum iteration. Next, for the convergence curve, -1 is equal to alpha fit. Here we will store the first batch solution score in the convergence curve, and then we will repeat the loop until the stopping condition is met. And in the end we will return best solution, that is alpha fitness, best position, that is alpha position, and convergence curve. Now we will define here the objective function and other parameters: population size, maximum number of iteration, lower bound and upper bound. It will directly run this. So here we will define the first function. Function name we have f1x. It will return the value that is calculated by this formula, np.sum x square. The function name we have f1. Lower bound for this we have -100, upper bound we have 100, population size we have suppose 100, maximum iteration suppose 100, dimension for this we have 30. Now we'll call this main function, that is calculating the fitness value, position and all. So here it will return best fitness value and best position and the convergence curve. That is GWO, and we have different parameters for this: population size, maximum number of iteration, certain input parameters, lower bound, upper bound, dimension, the objective function. Here we have function name. It will print best fitness is equal to, we have best fit, and we will print the best position that is equal to best position, and in the message box we will display the final solution. The root we have tk.tk and root dot withdraw Then we have message box dot show info. So here we will display the GWO optimizer result. That is, we have best fitness, and best fitness we have in this variable, that is best fit. In the new line, display the best position, that is best position. Now we will plot the convergence curve. So we have plt dot, we will plot here the convergence curve. On the x label we have iterations, and on the y label we have fitness. This title we have convergence curve. Next, grid true, then plot, then we will show the convergence curve. Done. Plus, so now we corrected here the slight error. Here we have into, and then here we have the plus sign. Now run the code. You can see here we have the GWO optimizer result. In the message box we have the best fitness and the best position, and here we have the convergence curve, and you can see here, and you can see here we have the best fitness and the best fitness and the best position. We can change the parameters here. Instead of this, we can apply 200. Population size, suppose we have again 200. Maximum iteration 500. Now you can see again convergence curve and all. Next, suppose we have population 20. Done. So now you can see here step by step we implemented GWO optimizer in Python. So that's all about this video. If you have any question, you can comment below, and thanks for watching this video.